Welcome back, welcome back, welcome back. I'm Miss Lisa. This is my YouTube video channel. I want you to like, share, and subscribe. I have goals. Everyone does. Mine is to not have to videotape then upload. I just want to upload. This is physical science. So on my channel, we talk about math and high school math and science, and this is physical science. This is a class primarily designed for homeschoolers, but if you like the way I explain things, come on in. We're going to talk about waves. We're going through this book, but you don't have to have this book to understand these concepts. So, this book starts with what is a wave, and I think their definition is interesting. And I thought, I don't know that I've ever heard it described like that. And I went back and looked at the other physical science book, and I noticed they didn't really tell you what a wave is. They just expected you to know from your common everyday life, which most of you already do. But this is what this book says. It says a wave is a repeating disturbance or movement that transfers energy through matter or space. There you go. So a wave. We're not talking about, hey, we're talking about a wave. So it is a repeating disturbance. And there's a relationship between waves and energy. So there are two kinds of waves. There are compression waves, where if you take your slinky, y'all know what I'm talking about, and you do this, it makes the coils get closer and farther apart, and closer and farther apart. That's a compression wave, and it's what sound is. Sound is a compression wave, not on a slinky, but it goes out in all directions as the molecules, the air molecules, are compressed and they move farther apart as they're disturbed by the vibrations caused by whatever is making the sound. The other kind of wave is this kind. This is called a transverse wave, and this is like your ocean wave going up and down, and it has high parts that are called peaks, and it has or crest, and low parts that are called troughs. The compression waves has compressions where the things are closer together, and rarefactions, that's fun to say, where they're further apart. Another property of waves is wavelength. And for a transverse wave, you ever done that in the car? Stuck your arm out and fell to the breeze and made waves with your hand? So, transverse wave, the wavelength is the measurement from peak to peak or trough to trough, from crest to crest or trough to trough. And it's symbolized, wavelength is this cool little thing here. It is a Greek letter, that makes you feel smart, called lambda. It looks like a little upside down Y or a teepee or a hat. The wavelength in the compression waves is from compression to compression, but it still has a wavelength. How often these waves come is called the frequency. It's written with a curvy F, the symbol for it. And the time period that it takes is called the period, and it is it's symbolized by a capital T. Another property of waves is the speed, but instead of saying speed, because that doesn't sound very fancy, we call it velocity, and the symbol is this V that's flat on one side and kind of rounded on the other. So there will be a second video to this one where we do a math problem. I think it's only one, but there will be a part 2 video with the math problem where we're going to calculate wave speed. All right, so look in your book. Let's talk about one other thing. Okay, so everybody think about when you were in a raft. You were like, maybe you had your floaties on, or you had an inner tube around you, and the waves come by. Do you go with the waves or sit where you are and bob up and down? You sit where you are and you bob up and down, right? The only way to ride on the wave is if you get like your boogie board and you look behind you, and then as the wave's coming, you push yourself just to get on that crest of the wave, and then put your boogie, like if the wave's here, you got to put your boogie board toward the front of it like that, and then it will push you all the way into the shore. So fun. I've done that for hours and hours and hours, to the point where you go back to your hotel. I don't live near the ocean. And you get in bed and you still feel those waves. I love the ocean. I haven't been there in a long time, but last time we went, it was to the Gulf, and it was like a lake. There weren't any waves. It wasn't fun. I like the Atlantic side, and I've never seen the Pacific, so I don't know about that. But I like the waves. I think they're fun to ride. All right, so the point is that a wave does not... the wave is the energy. The energy passes. It is not really that all the matter, the molecules don't go with the wave. The energy passes through the molecules. The molecules bob up and down, just like you did with your little floaties on or in your inner tube when this happened to you. The molecules bob up and down. The energy is what moves. So you have to realize that. So what waves travel through is called the medium, and the medium makes a difference in the speed. And one kind of wave is sound waves. So sound travels through air, and as well we're used to hearing it. Do you think sound travels most fast through air, water, or a solid thing? You're wrong. No, maybe you said it right. It actually moves fastest through a solid, second through a liquid, and slowest through air. And the reason why is because the particles are further apart. So it takes longer in the air for the energy to transfer. When the particles are really close, then the energy can transfer better, longer, faster. And if you've been to the lake, you might have noticed this. You're at the lake, you're swimming, and your head is above the water, and it sounds quiet. It's so peaceful and quiet. And then you go under the water, and you hear, ee, which is a boat. And you go back up to see the boat. There is no boat. You go back under the water, ee, you can hear the boat. And it's because the sound is traveling better in the water. Also, there used to be like Western movies, and there would be a Native American, and there would be a non-Native American, a cowboy, and they would be wondering when the train was coming. When's the train going to come? And the Native American wisely would put their ear on the track, and they could hear the train. You couldn't hear the train in the air because it doesn't make the sound as good, but you could hear it through the track. Now, do I think you should go lay your head on a railroad track? Absolutely not. Do not get squished your head by a train. You never know when the bullet train's coming. It's going to run over your head. So don't do that. Just know what the wise Native American is doing in the movie. Because sound actually travels better. And there's a lab that you're going to do with it in the other book. Remember, we got our regular book and our lab book, and we've got some good sound labs that you're going to do this week. And it's going to be great. You're going to love it. Remember, I've told you, you don't have to do these chapters one a week. If there are good labs and a lot of labs, you can spend more time with it. Like last chapter about fossil fuels, there's not much. There's like one little pinwheel lab. There's not much to it. But this one, there's quite a few labs that we can do with sound. So you might want to spend a little longer. This book, I think, has, anyway, less chapters. And I'm going to do the videos one a week. But you can go slower. And if I were you, I would. And I would definitely, if you live in the Atlanta area and COVID goes away, so museums open again, I would definitely go to Fernbank and toward the end of the year and go to their physical science room. They have a hands-on science experiment room where you can go around and do all these really cool experiments that we're going to talk about in physical science that you wouldn't have the equipment to do. So do all the labs we do, and then go do the field trip to Fernbank and go to the science room. And then, of course, while you're there, you have to go look at the dinosaurs too, because they're so cool. My favorite's the Argentinosaurus. It's so big. Anyway, I like all the Georgia one too, where you get to walk through the thing. And those of you who aren't from Georgia, look it up. There's probably a science center near you where you can do these same labs. All right. So your book talks about how ocean waves aren't purely transverse waves, that there's other forces, and what causes them, they believe, it has a lot to do with wind. It also has to do with the topography underneath the ocean as the water is coming against that topography, and it also has to do with the tides and the moon. So there is a lot to do with waves. Seismic waves are another one that come from earthquakes. I've been in several earthquakes and not even realized it, because I'm in Georgia where we don't really have them. But one time we had one, and it was when my son Joshua was maybe about 5 years old, and I was in the kitchen, and we have a few steps up to the level where the bedrooms are, and I hear boom, 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 and I'm like, Joshua, did you fall down the stairs? I don't know why I thought it was him. He's like, no, Mom, I'm fine. It was the earthquake. It made a boom, boom, boom sound, and it made a few things fall, and that was our earthquake. But I had a friend that I used to teach with back the first time I taught public school, and she was from California, and they would have earthquakes all the time. And when they would have earthquakes, she would run to the top floor of their multi-story house and jump in a rocking chair, and the earthquake would shake the house and make the chair rock like crazy, and she'd just ride the chair rocking across the third floor, riding the earthquake. She thought earthquakes were great fun. It was like free Disneyland. Run to the attic, get in the chair, and sit there and ride in the rocking chair. Now, is that what you were supposed to do in earthquakes? No, you're supposed to get out of the building so it doesn't collapse on you. Or if you don't have time to do that, you're supposed to stand in a doorway. Doorways are stronger. They're reinforced. You're supposed to stand in one. She said that's not what they did. That they got too used to them, and then they'd go run and ride in the rocking chair instead. She also said they had a lemon tree outside of their house with giant lemons on it and avocados. And it's like, wow, that's so fun. We don't have those here. We have I have a fig tree. It's got figs on it. It's real good. And I have a blueberry bush that makes lots of blueberries, but not avocados or lemons. I'm allergic to lemons, so that's okay. All right, so you're going to be getting out your slinky, and I want you to get a slinky. You can get them at the Dollar Tree for $1. I want you to make compression waves. I want you to make transverse waves. I want you to think about these things and do that. All right, the period of the wave, I don't know if I was clear about that, is the time that it takes one wavelength to pass a point. So that's the period. And as the frequency increases, the period decreases because it's getting a shorter period there. So wavelength is related to frequency. Wave speed is how fast it travels. And our math problem we're going to do is we're going to do one calculating wave speed when you come back. Now the next thing about waves is how tall they are. And the height of it is the amplitude. So like if these are where you are turning up the volume on your stereo, you increase the amplitude, because even though what is eventually produced is sound, compression waves, that it is electrical waves that have amplitude that is how the music is recorded, and then it gets translated into sound. So that amplitude, so sometimes you'll hear something that makes transverse electrical waves have a greater amplitude. You'll hear it called an amp. I got to go buy a new amp for my stereo. That means you're going to have this thing that's going to make the electricity waves taller, so that therefore you can get more sound or clearer sound without distortion as you turn it up. So that is what amplitude is. All right, that was section 1 and 2. The next thing is that waves can be reflected. Sound waves can be reflected as an echo. Sight waves. Light is transverse waves. I don't know if I told you that, but light goes in transverse waves. And in fact, the whole electromagnetic spectrum. Ronald McDonald is very ugly, extra gross. Radio waves, microwaves, Ronald McDonald is infrared, very visible, ugly, UV, extra, X-rays, gross, gamma rays. So all of those waves are given off by the sun and other stars, and they are transverse waves. Light waves are transverse waves, and they can be reflected. And you know that because you've looked in the mirror before, where light bounces off you to the mirror and then back to your eye so you can see you. And we have a picture of a guy holding a mirror and looking at himself in the book. Another thing you might have done is you might have done this with a laser pointer or a flashlight. If you have a mirror and you shine a light down on it, then it bounces off. And the rule is the law of reflection, is the angle it comes in at is the angle it goes out at. It's the angle of incident equals the angle of reflection, meaning that they bounce off. You can draw a perpendicular to your mirror, and it's called the normal. And all of these angles are symmetrical and the same on both sides of the normal. If you take physics from me, we'll do lots of fun math with that. But right now you can just learn about them because you're in physical science, and it's making you go, oh yay, I'm in physical science. I don't have to do all the math. Another thing that can happen with light, besides being reflected, is it can be bent. It can be refracted. So light is refracted when it moves from one medium to another. You've seen this before. You've seen a straw in a glass of water, and it looks like it goes down here, and then it looks like it scoots over here, and it's not connected anymore where it's at the surface of the water. And that is refraction. It's bending the light as it changes mediums. One way to think about it is like if you have a car, little car, and it is going along the floor and it hits the carpet, but it hits the carpet not straight on, it hits it at an angle. Then when it hits it, it's going to turn. And it's because the speed changes of the light as it goes to a different medium, just like the speed of the wheels of the car change as it hits the different medium of the floor versus the carpet. Your other book explains this really well. This might be one chapter you want to read in both books and not just do the lab in the other book. Because this one's good, but I think that other one might be better in this chapter. Another property that these waves can do is something called diffraction. And diffraction is where the way waves will go around things, they'll be disturbed by things, or they can go through a little slit. So you might have seen this before, where waves are coming at the ocean and there's some sort of wall with a little hole in it, and then they'll come out the other side, but they'll come in straight lines, they'll go out in little circles. And it is the wave will bend as it goes around a little slit. So this book talks a lot about that, about how the waves can get bent with things like that. Another idea is interference, and this is what it is. If you have, let's see if I can get my hand the right way where you can kind of see it. Kind of like that. Okay, you got two waves going along. You have one going up and one going down, and they go along, go along, go along. When they hit each other, they'll cancel each other out for a second, and it'll be flat, and then they'll keep going their own way. The waves can cancel each other out. If you have a crest meet a trough, maybe like that, a crest meets a trough, they'll go flat and then they'll just keep going their way. If you have two crests come along, see if I can turn it to look. You have two crests come along, they hit each other right when they hit, one will jump on top of the other one, it'll be twice as tall, and then they'll head off their merry way being the same size. Same thing if you have two troughs. One trough's heading for the other one, they hit each other, they'll become twice as deep for just a second, and then head on off their merry way. So it can either be constructive interference, where it ends up on top of each other, or destructive interference, where they flatten each other out. They cancel each other out. So that's interesting. Another idea with waves is music, and in particular standing waves. If you have a guitar string and you pluck it, it would vibrate up and down, back and forth. If you are doing a chord and you push on it, then this half will go up and down, and this half will end up going up and down, and there'll be this place in the middle where nothing is moving up and down. It's called a node, N-O-D-E. I don't think it's in this book. It might be in the other book. But, so a wave, that's something that's going like a jump rope all the way up and down, can be broken into little waves where there's like, it'd be like, imagine you had a jump rope going around, but someone decides to hold the middle and make it two jump ropes, one over here and one over there. That's what these waves do. There are things that have natural frequencies, like a pipe organ. The pipe is a certain length. As the sound goes through there, then the wavelength will have a certain length, and it will have certain places where the wave isn't there anymore, where the note is. And in it are these standing waves. They don't really move up and down. They're just where they are. They are standing waves. And it has a lot to do with music and sound. And it's how the length of things make different sounds in music. You've seen this before. You've taken a rubber band and you plucked it and it goes bloop. And then you make it shorter and you pluck it again, it goes bloop. And then you pluck it again, it goes bleep. And you're changing the length and it changes the wave and it changes the sound. Another property is called resonance. And what it is that one thing vibrating can make another thing vibrate. And it's like the opera singer singing at a glass, ah, and when they hit the right note, to make the glass start vibrating, it can shatter the glass. They did that on Mythbusters. They got a rock singer to do it. He sang at it and broke the glass. But materials have a natural frequency. It is their natural resonance. And if you can get it to start vibrating at that frequency, sometimes things happen, like the glass shattering. A long time ago, my dad had a car. It was a Dodge Dart, an old Dodge Dart where you change gears on the column. Had 3 on the tree is what they call it. But instead of having the gears down here, the gears were around there that you would do. And I would drive it until it got wrecked one day. But it was very fun to drive. And it was easy to drive. It was the easiest stick shift car you've ever driven. But it had a natural resonance, which when it got to 55 miles an hour, the whole thing would just start shaking. But if you could speed up and get past that, it'd quit shaking. Or if you got less than that, it'd quit shaking. But it had its natural frequency, was the frequency it would hit at 55 miles an hour. And if you stayed there, that car would just about shake itself to pieces. So things have natural frequencies. Another place where you've seen this and you didn't really think about it was the swing set. That if one person's swinging on the swing set and there's an empty swing, it'll start swinging too, because that energy will transfer and it's starting to hit its natural frequency. And even though nobody's in it, that swing will start going also. So these are great, interesting ideas. Come back and we'll do that one math problem that's on page 299. And where we're going from waves is we're eventually going to be talking about more in detail about sound and light. So science is great. I'm Miss Lisa. Like, share, subscribe, and I'll see you next time.